Okay, open back up your California housing notebook. Um, and what I want to do now is build a machine learning model. Okay, before building it, you've got to know what we're trying to do here. So here's all the data, if you scroll up to the top actually. And with machine learning, you're trying to predict one column from all the others. Okay, and in this case, the standard is to predict median house value. You could actually pick any column that you want. Okay, but this one makes the most sense because, right, the idea is you can use it for like real estate. If how much is the house going to sell for, and you could use the other columns to help predict that. Okay, so it's a big topic, in the world today. If you go online and you look at like how much is the house worth and all that, they're all using machine learning these days. So how are we going to do that? Well, the first thing we need to do is split the data into X and Y. So one other thing, I haven't put any text headers in there. Let's do that also. Let's get used to how Colab works. So if I click on this top coding cell, and I do this plus text, do this with me. It goes down here, but I want it at the top. See these arrows? You can move it up to the top. By the way, that's how you'd comment on a cell. And then, sometimes I try to double click, it doesn't work, but, or I mean enter. Yeah. Okay, so put in a hashtag and then load data. Okay, so that's, and then press shift enter. And then this idea, look at this arrow. You can like organize your notebooks like this with headers. Okay, so we load the data. And now I think what we want to do is, sometimes it's unclear where if splitting the data should go here or elsewhere. Let's do it in a new text header. I'm just going to call this one machine learning. Okay, so I got a second header here, second topic. You can press shift enter to run it. And then what are we going to do? We're going to split data into X, the predictor columns. Okay, those are what we're going to use to try to make the predictions. And Y, it's called the target column, what we're trying to predict. So Y is the last column and X is all the others. So let me show you to do that. So Y is the last column. Well, you can use Y equals DF. And then what was it? Median house value. So that's the last column. And now X is all the others. So how do you do that? You can use slicing, but you want to use index slicing. Okay, so it's something like this. df.iloc, that stands for index location. Then you do all the rows, comma, all the columns leading up to but excluding the last one. Okay, -1 is the last column. Just to show you another way you can do this Y one is similar idea. df.iloc, index location, all the rows, comma, but only the last column. Okay, so those are equivalent for Y. All right, and what you'll find is that it is not always the case, but it's standard that, hey, the column that I'm trying to predict is the last one, so this df.iloc Y and X string will often work. Okay, I tend to use it a lot. I used it so much last year, people didn't know that there was a different way to do it. Okay, I'll just put a note here. Second way to access Y. Y is last column. And then this one is basically, all columns except last, okay? All right, so that's X and Y. You can check it if you want X.head, Y.head. Okay, it's kind of fun. I'm gonna press shift enter and run it and just move on. Okay, so time to build something. Let's build a linear regression model, okay? That's the standard. I'm going to show you guys the math behind linear regression second half of today. So how do we do it? You got to get it, okay? Everything's split into libraries. So from sklearn, this is scikit-learn, which we'll use this first couple days just to get you grounded in machine learning. So it's from sklearn.linear model, okay? And then import linear regression, okay? By the way, why regression? This is important. So if you look at Y, well here, let's look at it. There are a lot of ways you can look at Y. You can just put Y in, and it shows you the first 5 and like the last 5. So this is a range of values. In And they could kind of be anything. I mean, yeah, they're rounded and, but that fits regression because regression answers the question, how much, like how many? And it's not like classification where you're splitting it up into just two, like which color is it? Okay. So whenever it's like a bunch of values that are numerical, where they're greater than or less than each other, you want regression. Not necessarily linear regression, but it's a regression machine learning model. Okay, I'm going to label this show why. Okay, so how do we do it? Here's the steps. This is like a preliminary step. So you import the model. I guess it's essential. Give it number 1, import the model. Number 2, fit model to data. No, sorry, I'm jumping ahead. Really, you should initialize the model. Then we'll fit it to data. So how do you do that? Model equals, and then put in linear regression, parentheses. Doesn't do anything. It's just kind of like, okay, we're ready to go now. We've got a model that's going to do linear regression. Okay. Next, now we want to fit model to data. This is all the machine learning right here. This is it. This is the magic line. Simply model.fit, and you put an x, comma, y. So what's the idea? It's fitting those columns, the x columns, to try to match it with the output of y. And linear regression is trying to find the mathematical weights, the multipliers, saying, hey, what can I multiply the columns by and add them together to get the right values? It's going to go through a bunch of iterations to try to find the best possible value. Now, if it's, I mean, with a linear model, you can only sometimes do so well, but, we'll see. So how do you see how well it did? You've got to score the model. Now, there are different ways to score a model, and you can just do model.score. Let's start with that. And so you can say, okay, well, what kind of a score did we get? Okay, press Shift Enter and run that cell. And by the way, I like you all to sometimes have first look. That score, the default is R2. It's R squared. And it's kind of like how much of how well the data fits the line. You could kind of think of it like correlation in the sense that 1 is perfect, 0 is awful, but you can get negatives like it's opposite, which is worse than no pattern. It gets 0.64. So, it's, how good is that? It's a little bit hard to say. Frankly, it's not the best scoring metric. But I want to show you this. From sklearn, let's try another model. From sklearn.tree, import decision tree regressor. Okay, it's got to be regressor, not the classifier, because again, as mentioned, the output column, the y column, is a regressor. If all the values were 0 or 1, like yes or no, then you would want the classifier, because it classifies into like 2 separate groups or more separate groups that are not quantifiable. So we want a decision tree regressor. You may wonder, some of you, what is that? It's like a game of 20 questions or 200 or 2,000. It just says something like this. If you look at our data, where's the data? It's way up at the top. We just need the columns. Like, hey, if the housing median age is greater than 15, then we split the data, okay? And then you keep splitting it based on questions. Okay, so at the end you can say, well, if the housing median age is greater than 15, the total rooms are over 2,000, the total bedrooms are over 200, the population is over 750, etc., then the median house value should be 150,000, something like that, okay? And obviously when you're doing it via machine learning, it's doing a lot of rounds and going back and trying to find optimal splits, okay? So the steps then would be the same, okay? So do the same steps here, okay? See if you can do it on your own without me. You're just looking above and copying it in, but you're like, instead of linear regression, I want to put in the decision tree regressor. And then because I call it model, everything else is the same, okay? So you fit it on X and Y, score it on X and Y. Let's see how you do. What'd you get? Did you get better than 0.64? Let's see. Oh my goodness, we got a 1.0. Decision trees. Okay, every time you get 1.0, a perfect score in machine learning, there's a problem. Now, sometimes, yes, you can get perfect predictions, it's true. But more often than not, there might be an issue here. So put in the chat if you know what the issue is. Okay, I'm going to title this cell build and score decision tree model. Huge concept here. Huge. Okay, we gotta get it. So maybe I know some of you have had this before. We're scoring it on the same data that we're fitting it to. That's a problem. Okay, you don't believe me? Look, machine learning is about how well it does a new data, right? You may have built a car that drives perfectly on like all the past trips. What matters is how well it's going to drive when a real person uses it in a future trip, right? So the idea is to test on data it's never seen before. Well, look at this. Go back in here. There's a California housing test set. Let's load this, okay? Put in, copy the path, okay? So access California test data. Let's see how the decision tree does, okay? Let me try it on your own. I'll guide you on this one. So first thing you need to do is load in the data. And you can just go ahead and put it in there. You can write df equals pd.read underscore CSV, then inside of quotes, command V, put in what you just copied. Okay. I know before I said like data equals, and then we put the data in there, but it's the same thing, right? It's just, I usually do it the other way actually, because sometimes it's nice. It's easier to read if you have more variables to like be clear about what's happening. We don't need to show it here. It's going to be fine. But we do need to split it, okay? Let's split into an X test, which is going to be, oh yeah, don't call it DF here. I mean, you could rewrite it. But if you call it DF test, then we actually have access to both, okay? Right, what would that mean, a data frame, but it's the test set. So among that test set, you would split it the same way. All rows, comma, all columns, excluding the last one. And for Y, I made a little error there, and you see it? df test should be .iloc. All rows and just the last column, okay? So with that, it won't work if you don't put in iloc. Again, iloc stands for index location. It's numerical indices of the columns and rows. It's always rows, comma, columns. That's a standard in linear algebra as well. Okay, so that's good. That's really all we need. Press Shift Enter. Good, no errors. Get an error, don't worry about it. You can always like look at my code, or you can go back. Sometimes maybe you forgot the iloc or the comma. Don't worry, I'll be making errors, and you'll be seeing them. So we'll get better at correcting errors together. So what we want to do here, look, model has been saved. It's been fit to this X and Y. We simply want to see how well does decision tree model perform on test data. It has never seen, I'm emphasizing that. Test data means you've never seen it. Well, now we can check it. Model.score, and then you want to put an X test, comma, Y test. So what it's going to do there, right, the model's already been built, so it takes all its weights, multiplies them by the new rows in X test, and it's going to compare the results to the output of Y test. So how do you think it'll do? You think it'll get close to 1.0, or is it going to be like linear regression 0.64 or somewhere in the middle? Well, in machine learning, the name of the game is experimentation. Press Shift Enter. Oh my gosh, it is no better than linear regression. What is going on here? Okay, guys, this is a huge topic. And it's called overfitting the data. Decision trees overfit the data. Right? It's a game of 20 questions. Look, if there's how many rows were there? Was it 17,000? Let me show you how you can get the shape. df.shape. Okay. 17,000, yeah. So this gives you so it's rows, comma, columns. Get shape of data frame. Against rows, comma, columns. What this is telling us is that, or what I'm trying to tell you, look, if you've got 17,000 rows, like you could ask 17,000 questions and guarantee that decision tree is going to get it right. Because, you could ask it each little question and guarantee that you get the right prediction. But it's not going to generalize well the new data. It's too specific. Okay, we'll look more at that topic in detail throughout this class, actually, because overfitting the data is a big concept in machine learning. And it happens a lot because, the models are so good, they're basically too good. And if you want to just go back to the beginning, if you look at the neural network, if you still have it up, regularization is actually something that helps to prevent overfitting. This is interesting if you look at the test loss to the training loss. See how the test loss is higher than the training loss? What that means is the score is like worse on the test set than the training set. So you can put in a regularization rate of 0. It should have some I don't know what we should put in there for the rate. But that should help. You can try to run it. I mean, maybe the model's not getting a better score, but you can see that the test loss is a little closer. That might be too weak. And you could also try adding in some things like sin of x based on the data here. Yeah, you guys play around with it. You could probably do better than I can. But whatever the case, it does accomplish the goal. The test loss is better than the training loss. We'll figure it out together, okay? That's an introduction to machine learning. See you guys soon.